This Week in Virology, the podcast about viruses, the kind that make you sick. This Week in Virology, a special episode recorded on December 12th, 2012. That's right, it's 12/12/12. But it's not 12:12 p.m. It's about 4 p.m. here in New York City. Hi, everyone. I'm Vincent Racaniello, and you are listening to TWiV, the podcast all about viruses. Today I have a special episode for you. Consider it my holiday gift to everyone. It has nothing to do about viruses. It has to do all about ignorance. How about that? Is that a good teaser? My special guest today is Professor and Chair in the Department of Biological Sciences at Columbia University, Stuart Firestein. Welcome.
Well, thanks. It's very nice to be here.
Firestein or Firestein?
I say either or either.
You're
so
happy with either.
I can do either one.
Some people want it one way or the other.
My mother likes Firestein, so I guess we better go with that.
We have to please your mother. Firestein. Thanks for joining me today. You're a neuroscientist, right?
Yes.
You're not a virologist. Probably.
Nope.
Don't you ever have studied viruses, but I think you use the vectors at some point.
We use the vectors all the time. In fact, in my laboratory, that's right. Yeah,
right.
Viruses, the best little machines going.
Yeah, they're one of the questions I got at the Cafe Columbia this week was: is there any hope for using viruses as vectors to cure human diseases?
Well, that's a good idea.
Absolutely, for sure. I wanted to get you up here, not to talk about neuroscience, or I'm sure that'll come up, but to talk about a book you wrote, which caught my eye, I don't know, months ago, and I ended up reading it. I read it in 2 hours on an airplane going somewhere.
Perfect amount of time.
And that's exactly the way you want it, not to be a burden, and it was terrific. It's called Ignorance, How It Drives Science, right? And I thought you and I could talk about it and give our listeners a flavor and explore some of the points in your book. It's a great title. And, in fact, I picked it on This Week in Virology a while ago as a listener pick. We do, not a listener pick, as a pick. We each pick something every week that we think the listeners will like, and books, movies, whatever, anything. And that was my pick. So hopefully some listeners have read it.
That'd be great.
And if not, after this episode, you'll want to read it. So I thought whenever I have guests, I always start out with them telling their story. And in fact, one of the chapters in the book is you telling your story. And I enjoyed that a lot.
Well, thanks. It's a little bit of an unusual story, I guess. I don't need to retell it entirely here.
Give us the overview.
I will. So the idea, of course, in the book is at least the second half of the book are what I call these case histories or case histories in ignorance. The book, of course, is all based on a course that I started teaching here at Columbia some years ago, and we can talk a little bit more about that in a moment. And part of the course has these, I invite people in to talk, and then I use these case histories, as I call them, to demonstrate some of the points in the book. So I did 3 of them, and I wanted to have a fourth one. It seemed that there was one missing somehow or another, and I kept thinking, I don't know, I can't figure out which one it is I exactly want to do. And at one point, my wife, somebody who was due to come into the course one week, couldn't make it at the last minute. I think they were injured in a skiing accident, some crazy thing. Anyway, they couldn't make it at the last minute, and my wife, who's also a scientist, said, well, why don't you do it? Why don't you be the guest, and I'll interview you? And I said, well, all right, I guess we could try that and see how it works. So I based on that, and then, of course, the fact that I know my life, I thought, well, and then she suggested, while I was writing the book, she said, well, why don't you use yourself for a case history and see how that goes? So I thought, all right, I have a slightly unusual background for scientists in that I started life, really, my professional life anyway, working in the theater. I was a stage manager. I mean, I started out as an apprentice and a stagehand and a sound technician, lighting technician, stage manager eventually, and finally a director, which is what I mostly made a career in.
Where did you grow up, in the New York area?
I grew up, I was born and raised in Philadelphia. Then I was sort of in New York, and then in Baltimore, Washington, a little bit in Boston. I sort of consider the Northeast Amtrak corridor my hometown.
Okay.
So, and in those days, in the days that I was working in the theater, now this is in I'd say the 1970s. My God, that sounds quite a ways back, doesn't it? But in the 1970s, the big thing really was to decentralize theater in America. We had all these regional rep companies. The idea was to move theater out of New York City and into the provinces,
like
as
baseball,
it were.
Right?
Yeah, very much. get it out there, or the National Hockey League. That hasn't worked out so well, but
Yeah, baseball. We used to have all three teams.
All three teams here. That's right. So I did a lot of work in these so-called regional repertoire companies, which was actually quite nice. It was a great way to do the theater and a little less commercially oriented and therefore a little less frazzled. I did some commercial work as well, and I was always happy to do that. But so I got a chance to do a lot of different things. And then I wound up moving to San Francisco with a show, actually, and I liked it out there, and I stayed there for a while and got involved in the theater scene there. And picked up another show there, which I did the lighting for, actually, and then they wanted me to run the show, that is, be at each performance and do the lighting for the performance. And it got very good reviews, looked like it was going to run for a while, so I thought, all right, I have a cushy little job here for a while, a little more stability than I was used to. And I'd always had this interest in animal behavior, so I went off and decided I'm going to take a course at the local state university. That's California State University in San Francisco. And in those days, you could actually be a full-time student at Cal State San Francisco for $106 a semester. Now, that's not just an inflation issue, I have to say. There's a lot of other things that have happened that have made education much less accessible monetarily than it was then, and I think that's very unfortunate. But for me, there was no issue. I mean, money was not at all a question, financial aid, it's $106. I mean, come on. Sure. And somebody stands up and tells you everything they know about something. I thought, well, this is a great idea. Who thought of this? So I'm fond of saying I think it was Aristotle, but I hadn't heard about it yet. So the good part of this story, and I won't go into the lengthy part of it. You can read the book if you really want to hear the ugly details. The good part of the story is that I met a great mentor, a fellow named Hal Markowitz, who I'm sorry to say died 2 months ago. But he was a great mentor and a wonderful teacher. Yes, he did. He did read the book. He knew about the book and his dedication to him in the book, as well as two other mentors that I've had. So I've always been, I'd say, very lucky this way. I'd like to think it's not just luck, it's the way the system works. But I had a great mentor in Hal Markowitz who taught this course and convinced me to become a student, as it were, at 30 years old as an undergraduate, which seemed crazy, but he said, no. He helped me through all of that, and I did. And then I got an undergraduate degree in biology, which, as we all know, is worthless, but I didn't know that then. He never told me that. So then it came down to graduate school, and that's really when I had to make a decision that I was going to change my life or not. So I thought, because I could do undergraduate and still work in the theater and back and forth, but graduate school, as you know, is a commitment to a different level of what you're doing. So I applied to graduate schools and thought, well, if I get in, I'll do that, and I'll have a second career. We all live twice as long as we used to. Why not do a second thing? And if I don't, I'll go back and work in the theater happily with my undergraduate degree in biology. I fortunately got into Berkeley, which is, say regularly, is probably the result of a clerical error, but that's all right. Take advantage of those two. Where I met another great mentor, Frank Werblin, who's still a very close friend at Berkeley. He's still there. And he took me into his lab as a 35-year-old graduate student, which I now recognize, running a lab myself, you have to be a little crazy to even consider that, but he did. And he was just a fabulous trainer. And then I went on to do a postdoc at Yale University with Gordon Shepherd, another fabulous mentor. People who really, it always seemed to me, had, my career and what I was doing mostly at heart. And I guess I say I think I was lucky that way, because you hear these horror stories so often about, bad mentoring or PIs lab heads that steal ideas from people or try and get credit or this or that. And I have to say I was fortunate never to have seen that or experienced it. And it's made all the difference. I mean, it's permitted me to have a wonderful career. So I'm a firm believer in mentorship.
So after your postdoc, did you come to Columbia, or were you somewhere else before that?
No, I was a postdoc at Yale for 2 years, really, and then they put me up into one of these research assistant professor type positions. Okay. And I established a lab there, more or less independent lab, for 3 years. And then an opportunity came up at Columbia, and
when was that?
I came here. That was in 1993.
Okay.
And once again, I had a great mentor, actually. I came here as a non-tenured associate professor. Darcy Kelly, who's in our Department of Biology still, a close colleague, brought me in, and Marty Chalfie, who was also a close colleague. The two of them were instrumental in bringing me into Columbia and in mentoring me through the whole tenure process and everything else.
So you made that decision that you were going to quit the theater and go to graduate school.
Yeah.
So you quit, you let that play run out, that last one that you were doing?
Well, that had long gone, actually. This was already 4 years later. This was now after finishing undergraduate.
And
so I was
as
now
an undergrad,
34,
were you
35.
working in the theater?
I continued to work in the theater. I had this odd sort of flip thing because I would go to school during the day and work at night, whereas a lot of people, work during the day and go to school at night.
It's funny you mentioned lighting. So one of my co-hosts on This Week in Virology, this show, Rich Condit, his daughter does lighting.
Really?
She, I think she's in Texas now. So she's a professor but does shows, and she did the lighting for The Hood. Is that the one about Washington Heights?
Oh yeah. Yes, the Broadway show, right?
Yeah.
Yes.
And
yes,
Jersey
really.
Boys. And Jersey Boys.
Well,
so she's good.
She's pretty good. Oh, that's very fancy
I told
stuff.
him,
Yeah.
if we ever do video on TWiV, can she help? And he said she'll make you look like Johnny Depp. Which is not possible.
I would hire her right away.
That's a great story. So basically, I don't know if today you could do that, but I would say to people, if you want to do something and make a switch, just do it if you're passionate enough about it.
I think so. I think if you are passionate enough about it and you're willing to, stick with it, you can do it. But you have to find people to help you out. I don't think you do it on your own.
Right?
I think you need good mentors, and it's a responsibility we all have to be good mentors as well. I think it's not appreciated enough.
Sometimes we get letters from listeners who have bad mentors, and they want to know what to do. So probably they have to switch.
I think so. I mean, I don't think you change the spots on a leopard in that particular sense.
Really.
I think you just have to jettison that one and go on to someone else.
All right, let's talk about ignorance.
Okay.
I love the first quote. It's difficult to find a black cat in a dark room, especially when there is no cat.
Yeah, isn't that perfect description of science? Is that not what we do every day?
Yeah.
Yes.
That's a great one. Let's define ignorance, because as you say in the book, there are two different ways to look at it.
Yeah, so of course I use the idea of ignorance both as a course title and as a book title to be sort of intentionally provocative, I suppose. And
exactly.
I don't, of course, mean, yes, but I don't, of course, mean that kind of ignorance that's just simply a word for stupidity, or worse than that, a kind of willful stupidity, indifference to fact or data or empiricism. I think, the ignorant, I think we all agree, are unenlightened, unaware, uninformed, and unfortunately often occupy elected offices, but that's another story altogether, I guess. No, the kind of ignorance I mean, I think, is best expressed in another quote that I use in the book from James Clerk Maxwell, a physicist, perhaps the greatest physicist between Newton and Einstein, I guess some would say, who said that the prelude to every great discovery in science is thoroughly conscious ignorance. And that's the kind of ignorance that I think we mean, and I think he's absolutely right.
Was that your choice, or did your editor have that title for the book, Ignorance?
The title for the book was more or less my choice, Ignorance. The How It Drives Science was the editor's decision. They weren't sure how it would play otherwise, and I think they were probably right.
But your course had been named Ignorance long before that, right?
Yes, so the course had been running for about 4, almost 5 years before I actually dug in and wrote a book on it, and that's just called Ignorance. And I think it's called Ignorance, A Course About Science. Sometimes I'd subtitle it that so people have some idea what it's about.
I know you mentioned in your book that if you're taking a course in ignorance, is it good to get an A or an F?
Yeah, that always puzzles the students on the first day. We talk about grades. And I say, now you want to think carefully about this. In your transcript, it's going to say ignorance. You want to have an A or an F after that.
Right. That's great. That's a great course. So how does the course work? What do you do?
Well, the course is a seminar course, so it meets once a week for about 2 to 2.5 hours. I usually schedule in an evening because it seems to be easier to get people together then. So we meet from 6 to 8, usually on Wednesday evenings, doesn't really matter. So it's 15 times a year, basically, that the class meets. And in about half of those meetings, more or less, we discuss various bits of literature, both primary and books and things like that we read from. Questions like, are there limits to science? Can everything be known? What's a appropriate question for science. What's a fact? How long does a fact last? Do facts come undone? When do we think a job is finished? When do we don't? How might we decide about what questions to ask, or how do you make questions? Variety of things like this. Sort of a little bit of philosophy and history of science, although I'm neither a philosopher nor a historian of science, but we at least look over some of that kind of literature and have discussion about it in readings. And then on more or less alternate weeks, or the other half of the weeks, I invite members of our faculty, mostly Columbia, but not only. There are many other people in New York, of course, especially, and many people traveling through New York giving talks or at symposia, and if their schedule works out, I invite them. But I invite essentially a working scientist to come in and spend 2 to 2.5 hours talking with a group of students about what they don't know. Not what they do know, not the facts that they've published and discovered and all the rest of this, but what they're working on right now, how they chose that question as opposed to some other question that we also don't know, why this question is more important than that one, why it's more valuable, what will happen if you do get to know that question, what will happen if you don't get the answer to that.
But they have to give some background to their area, right?
So what I usually ask them to do is to suggest a sort of a review paper, a Scientific American level paper, a Discovery Magazine paper, not even necessarily one that they wrote, but just something about their general field. Usually it is something that they wrote, but it's not always. And I distribute that to the class. We talk about it with the class a little bit first, and then I do a little bit of a literature search on them. I get a couple of papers from them and do my best to read them. Sometimes I can read them quite easily because they're neuroscientists or biologists at least, and sometimes, I've had physicists and chemists and mathematicians and various kinds of engineers, and it's a little trickier to read their stuff, but you can do it. You can kind of get through it more or less enough anyway to get what the questions
So
are.
Before you have a guest in another class, you'll talk about their area? Is that it?
Yeah, usually we distribute the papers first. We talk a little bit about it the class before, and then I usually ask the students, we have all these, what we call it, Columbia courseworks. Every university has some web-based thing where the class can communicate with each other, where you can post various things for them to see and all the rest of that. And so I ask each student to come up with 1 or 2 questions that they might like to ask this person based on the readings and the discussion that we've already had, and to submit those 2 or 3 days before the actual class. And then I go through them, and then we, in fact, do that. And so we start the class off. It's a sort of it's like the actor's studio thing, except I'm not quite as creepy as that guy, I don't think, anyway. Well, we just sit at a table in the front of the room, the scientist and myself, and we begin a discussion. And very quickly, surprisingly quickly, students join in. They have questions. They want to know this. They want to know that. And I let the conversation wander more or less where it will, just like you're doing right now with this one.
Sure. How many students do you have in the class?
So that's a good question. The class started small and was intended to be small. And the first year we had 15 or 20 adventurous students who tried it. And then I guess a little bit of word got around. So I had a few more students the next year. And I typically cap the class at 30 students. When you post it online as they're available, you can check a box that says cap this class at 25 or 30 students, whatever it was. And that's what I'd done for a few years. It was getting 25 or 30 students, which seemed like a good number. And then one year, about 3 years ago, I apparently forgot to check the box. And the next day, the day after registration closed, I opened up the course site to see how many students there were and all that. And there were 95 students who had registered for the class. And I thought, oh boy, now I'm in deep here, So the class is only available to seniors. I make it a class for seniors, and it's in the spring semester, so it's their last semester there. So I felt bad about, it wasn't like I could go through the list and say, oh, well, all the juniors, I can write them and tell them to take it next year. Everybody was in their last semester. And I thought, gee, if these people really want to take the class, I'll try it with 90 students. And it worked out. Yeah. I was surprised, actually. In some ways, it worked a little bit better. The students are even more involved and more engaged in the discussion, ask more questions than in a smaller group, which at first surprised me. And then I don't really know the exact reason why, but I think the anonymity of being in a larger group helps a little bit, especially in a class where so seminar classes, if it's just me for 15 weeks, by the end of the second or third week, everybody's pretty comfy with me and they're willing to engage in discussion. But when you bring a perfect stranger in every other week, then the students have to sort of start that whole, well, is this guy or woman going to, take any kind of question, or do I have to be a little more formal with them?
Sure,
so I think it's easier actually in a larger class, and it seems to work. So I've left it that way.
I always wondered, because my class, my virology class, is growing every year in number, and I would like to have more discussion, but I always thought that having 80 or 90 students would prevent it. But from what you say, you can do it.
What's in the format that the ignorance class works in, you can. I mean, I also teach a large lecture class in neurobiology, and it's typically 90 to 110 or 120 students. And there I would say it's harder to have discussion.
Yeah.
It's more difficult. You can stop and ask for questions, and you'll get one or two, but it's hard to set up a serious discussion.
So I could come in and say, okay, I work on polio, and one of the questions that we don't know the answer to is how the virus gets into your nervous system. That would be okay. That's one of the things we don't know. Would I say how we try and answer the question then, or is that not part of it?
Sure. Yeah. No. You could. Yes, you could say we're trying these sorts of things, or these are the things we've tried. We've failed for how long now? I think an interesting corollary to ignorance, by the way, is failure.
Failure, sure.
The other thing that students ought to learn about science.
Yeah. Okay.
And so we often talk about that. And how many things have failed, how many things we were sure would work that haven't worked, how many things worked for a while, and then we learned actually that's not the way they worked, or they've come undone, or this or that.
Okay.
Yeah.
And how do you grade them?
Well, that's always a bit tricky. Mostly it's just I ask them to write a paper at the end of the semester. And the paper, I insist, first of all, because there are now 100 of them. There's only so many. And they're seniors, so I don't have much time to read them, actually, because they need a grade to graduate.
That's right.
So so I insist they write a 1,500-word paper. The reason for this is that Columbia students become extremely good at writing 5,000-word papers. That's the standard paper. So they've all learned. The one thing they learn at Columbia is how to bang out a 5,000-word paper. So 1,500-word paper is actually much more difficult. There's a famous phrase which has been attributed to many different people, from Abraham Lincoln to Voltaire to Ben Franklin, but I think it's actually Blaise Pascal. I sort of tracked this down a bit. And Pascal supposedly had written a rather long letter to a friend, and at the end of the letter he ended it by saying, I apologize for the length of this letter. I would have been briefer if I'd had more time.
I love it.
So that's perfect.
We use that sometimes when we get long letters on TWiV.
So 1,500 words is a little trickier, and then they're mostly graded on the paper, and it's not a tough grade. One of the reasons that I teach it for seniors and do it in the spring is that the grade doesn't really matter. I mean, this is a purely selfish reason, but by the time they're a senior, they're either in medical school or law school or business school or whatever graduate school they're interested in, or they have a job that they're going for. And how much can the 2 units of the class affect their GPA anyway? So,
do you take into consideration their class participation, as we call it?
Yes, I try to.
So you have to remember, but you get to know the people who talk a lot, right?
Yes, and of course, as is always the case, there are people who will talk a lot and people who will talk much less. And sometimes the people who talk less wind up emailing you later on, and they want to have an email discussion with you or something like that. And I appreciate that. Some people just are too shy to open their mouth in a big room full of people, and that's okay.
Okay. So what's your beef with facts? Tell us about that.
Yeah, well, I may have overstated it just a little bit.
It's okay. It's for a point. The same way that ignorance is a shock title, right?
Right. So I just feel it's a balance issue, really. I think that the part of the problem, one of the difficulties, is that science has become what I call runs on the accumulation model. It just seems to be an ever-expanding pile of facts, and it seems impregnable, I think, to most people, even to many scientists. I mean, Nature or Science comes every week, and you look through it, and you're lucky if you can really, understand 2 or 3 of the titles, let alone read the articles. So you begin to think, well, what can the public have to do with this? How can we provide some access to this? And I think it's wrong in the end. It's not really about piling up facts. For some reason or another, and we could go into whatever the sociological reasons are or theorize about them, science, I think, has turned this sort of encyclopedic face to the public, as though that's what we're all built about here, and that's what we all do, is we gather facts and we put them in encyclopedias or big textbooks or something. And we now hide the face of the mysterious part of the operation, the questioning part, which is what we all mostly care about. And so I guess just to try and balance the issue a little bit, I feel that it's a good idea to try and point out that science is much more about the questions than it is about the facts. And that in point of fact, if you'll pardon the phrase, I think most scientists recognize that the facts are probably the weakest link in the whole operation. I mean, facts change. We know that. That's what, for me, this is what makes science different than other belief systems, be it astrology or even some religions or things like that. And that is that in science, revision is a victory. That's what we work for. We try and revise. We overturn facts, or we at least revise them. Whereas it's an embarrassment in astrology if suddenly, something that's supposed to have been this way for 10,000 years is not this way anymore.
Right.
So that's the difference. And I think facts are a culprit in some way, that we can become too dedicated to them. I mean, you can even see it, I think, in your graduate students probably, that we don't really teach them enough about how to put a question together. And, the first thing they're worried about is how to do the experiment, how to get the fact, how to get this or that, how to fill in the bits in the table.
So my take on your book was there are two issues. There's facts in teaching and then facts in research, right?
Yes.
So we teach facts, and that's what
Yes.
got you to teach this ignorance course, because you said you were giving them too many facts, and at the end they said, do I need to know this for the exam?
Yes, and isn't that your typical experience? And you begin to wonder, is this what we ought to be teaching them? My favorite quote about education is from William Butler Yeats, that the purpose of education is not to fill buckets, it's to light fires.
Yeah.
And if all we're doing is filling buckets,
you're absolutely
especially
right.
in the age of Google and Wikipedia and whatever is going to follow it, facts are a click away.
I have to tell you, after I read your book, and I felt very badly about the way I teach my course, because I remember the first year I taught it. It was 3 years ago. Before the first midterm, the student says, a lot of material here. What do we have to know? So I had to give them a study sheet with the questions that would be on the exam, basically.
Yeah.
Or areas that would be on the exam. But that's giving them facts, right?
Yes.
How does this virus get into cells? What does it attach to? How does it make RNA? Maybe I should put a few questions in about what don't we know about this virus. Tell me one thing we don't know about polio.
I think that's a great idea.
Maybe that'd be a good question.
Yes, I think it would. I've often thought that we should have even a multiple choice exam, those little bubbles that you fill in.
Yeah.
There should be, in addition to A, B, C, and all of the above, or none of the above or something, there should be either I don't know or we don't know, and that should be a legitimate answer to a question.
Well, maybe if you get people like me to change their courses, that's a success, right?
Well, it's not easy, mind you. I mean, I think about it all the time, too. After all, of course, part of the problem is that both of us teach courses to students many of whom are pre-med, and many of whom are going to have to take an exam called the MCAT. And if you don't teach them this stuff that's going to be on the MCAT, they're not going to pass that exam. They're not going to get into medical school.
And the MCAT's all about facts, right?
And it's all about facts. So you have to change it really several levels up, which is not an easy trick, as you know. I mean, these things stay in place for years and years. And evaluation, I think, in general in education is maybe one of the most difficult problems around. From elementary and high school education, you see the problems we have with it now, trying to evaluate schools and people teaching to the test and using what I call the bulimic model of education. We jam a lot of facts down their throat.
And see who's the best at spitting them back.
Right, they throw it up on some exam, and then nobody gains any weight, really,
It's a problem with medical school in particular, because they apparently want just people who are really good at getting great grades.
Yes.
And that's not often going to be the best physician, I think. Right?
I think that's true.
I mean, you need some other kind of metric, and it's not just... I mean, I see, especially MD, PhD applicants up here.
Oh, yeah. Yeah, I bet that's...
the most overachievers I've ever seen in my life. They do everything.
Yes.
Makes me exhausted to read their CVs.
Yes, I know. How can you possibly do it? And you have the sense, though, that having done all the stuff on the CV, they've basically done it to build the CV.
Exactly.
That seems to be the motive. And that's what's disappointing,
and I get these kids
really,
to interview, and I often interview them. They're wonderful kids. They've done so many things, and they're really genuinely interested and engaged, but I just feel that they're not doing it for the right reason.
Yes, yeah. Yeah,
there's
this
something
is not something that really
missing.
tickles them in some way that they can't do anything else.
Unbelievable.
I once, when I was back in the theater, I took an acting class from an acting teacher. I wasn't sure there was going to be an actor, a director, or whatever. And I did okay as an actor. I did a little bit of acting here and there. But I remember this fellow telling me one time, he said, there's only one way to be an actor. The only way to be an actor is that you can't be anything else. If you cannot really see yourself living without acting, then you're an actor. Otherwise, it's way too frightening to do it. And
Same with science.
And I think that's exactly right.
Absolutely. That's what we've heard. Now we had a few people come through who have said the same thing. If you can't imagine yourself doing anything else, then you can be a scientist.
Yeah.
But if you can see doing something else, then
you'd better
maybe you should do something else, especially nowadays when it's very tough.
Yes.
So we really need to fix our teaching. We have to give them some facts because, as you say, you assign a review article so the students can then ask questions, right?
Yes.
Because questions come from having facts, and then you use them to tell you what you need to know, right?
Right. I mean, for me, the purpose of a fact, the purpose of course, we do science. We go after facts. We want data. That's what we go after. The question is, what are we going to use that? What do we do with those facts? And I think the best thing to do with those facts is to make better questions, that every fact really generates a few new questions, but better, as I say, better quality ignorance is the way I like to put it, because it sounds so silly in a way. But it's true. There is high quality ignorance and low quality ignorance, and that's what we think about all the time as scientists.
There was a quote you had, which was the best, the best research leads to more questions, not facts, right?
Yes.
Something like that.
Yes, yeah. I think George Bernard Shaw in A Toast to Einstein is one of the quotes that I use, which is science never solves anything. Every time it makes a discovery that just leads to 10 new questions or something to
That's
that
the way
effect.
it should be. But not all science is like that, right? There's some scientists who just try and accumulate facts.
Yes, and you can't completely dismiss that. I mean, there is some science that works by moving the decimal point one more notch, and adding something. One of my favorite examples of that kind of science, although it's somewhat imaginative in its own way as well, is Kepler. I mean, Kepler spent, I think, 6 years battling with 8 minutes of arc in the sky. The planets weren't going in perfect circles, and that was, by this time it had been reasonably well established in everybody's mind that, in fact, the planets went around the sun and not the other way around, but we still had the tyranny of the circle. People thought they went in circles, and you couldn't really work it all out until Kepler figured out the 8 minutes of arc that everything was off by was not an artifact, really careful measurements, and when he fixed that and realized the planets went in ellipses, then Newton made sense. Then it was possible for Newton. So, sometimes.
But his facts led to more questions.
Yes,
obviously,
absolutely.
And that's what is important.
Yes.
But as you say in the book, sometimes we reward facts, and that's part of the problem. So, grants and talks and papers in prestigious journals are based on presenting a set of facts, right?
Yes.
Cell and Nature and Science don't care about the next question. They want your paper.
They want your paper now. That's right. Of course, if you're clever somehow or another, or if you're good at this, or if you've gained enough confidence to do it, you try and leave the paper with a question. You try and end the paper with a question or something like that, or a suggestion about where it'll go. Yeah, I've always thought, I assume many of your listeners will know this as well, but in addition to the papers that come out in Nature and Science, they're often, sort of what they call commentary type articles, news and views or this or that, where they ask somebody else in the field to write a commentary about this really interesting paper in that particular issue of Nature. And I've always felt I prefer to write the commentary.
Yeah, the author should, right?
I hate handing in a paper, though. Not that I get so many papers published in Nature and Science, but the couple of occasions I had, and I thought, gee, what I really want to do is write the commentary. They give me 1,000 miserable words. All I can do is dump a lot of facts out in this, and there's no time for me to pose the interesting questions that I think it's about.
Right, and probably they're different from what the other people are writing in their news and views, right?
Yeah. So
I always wonder how often do the authors of the article look at those and say, well, these are good, but I have some others as well. It would make more sense, wouldn't it?
It would.
Right?
Well, it's a perfect example in many ways of, I would say in some ways, what's exactly wrong with science. So you take journals like Nature or Science, which purport to be general interest journals, right? I mean, part of the deal of publishing a paper in Nature is it's supposed to be of interest to a wide audience, or a relatively wide audience, not a narrow, specialized audience. And then they tell you, but you only have 1,000 words, and you only have one paragraph for an introduction and one paragraph for a discussion.
It's crazy.
It should be just the opposite of anything. I mean, 1,000 words is bad enough, but okay, let's go with 1,000 words because there's a space problem. But then it should be mostly introduction and mostly discussion and a couple of facts in the middle. And if you want to look some more up, go to go online or whatever you need to do. But it's just the opposite, really, of what it should be for a general audience to understand it. And that's why none of us can read those papers.
I had a colleague here years ago, R. Jeff Stratiadis. I don't know if you know the name.
I don't remember that.
He was right next to me, and he used to complain that you can't write scholarly papers anymore because you have to be so short. And in fact, now where everything is online, I don't see why you can't.
I don't see either. Right. I mean, space is not an issue.
There is a new journal, eLife.
By
the Howard Hughes and Wellcome.
Max Planck and Wellcome,
And they're supposedly allowing you to run wild with your words.
Oh, that's interesting. I've had a sort of I'm tried to pitch this a couple of times to one publisher or another. I'm still hoping the Columbia University Press may do it one time. I think it would be interesting to take the 10, quote, best papers of the year, however you want to judge that. I don't know if you can put a committee together or whatever you want, but papers that were in Science or Nature or any of these other sort of high-end journals that have serious restrictions on space, though. And then go back to those authors and ask them if they would be interested in writing a somewhat longer article with the help of a writer, if you want, a science writer, that really let them kind of develop the ideas in the paper more, that really explained a lot about the paper, that gave some background on the paper, that talked about where they hope to go with it or how they came to it or things of that nature. And I suspect there'd be an audience for this. I think it'd be fascinating to have this wider view of these really interesting papers.
It's a good idea.
And you could bring this out once a year.
Absolutely. It's a great idea. I like that. One of our colleagues in the city, Arturo Casadeval, he's a chair of micro at Einstein.
Yeah,
he and a colleague of his, Ferric Fang, wrote 2 papers about what's wrong with science and how to fix it not too long ago. Reforming Science, they were both called. And one of the issues he talked about was that we have too much competition, and that leads to imbalances and fraud and all the bad things in science. And that's because we have competition for papers in the best journals, for grants, for Nobel Prizes and other kinds of prizes. But really, those are all competitions for facts, right?
I guess they are, yes. I mean, that is the problem at the base of it, yes. It seems like it used to be less competitive and somewhat more maybe collegial, and I guess the reason for that is that at one time there seemed to be more money around. Maybe there were just fewer of us doing it, and so there was more money around. Science wasn't quite as expensive as it's gotten now, and so you could run it on less money and all. But of course, that's always the case. I mean, when the money runs short, then everything else becomes extremely competitive, and probably not for the best purposes. I think that's right.
I just think that in light of your ideas about finding out things that lead to more questions, maybe those aren't the findings that always get rewarded, right?
Well, I think they're often not. Certainly the questions, you rarely get rewarded for the questions. You know that. And of course, people want things settled.
Right.
But that's not the way science works. Science doesn't settle things. And this is the one area I must say that were I to write the book again, I would write another chunk of it that I think I probably left out and should have spent some more time on, and that's this notion of uncertainty and doubt in science, because it's become very important in things like the climate issue, where there are those forces that, for their own purposes, that would try and so-called deny the issues of global warming and so forth, and they do it by claiming, well, we just don't know enough yet. The science is too uncertain, or this or that, and because scientists are, to be honest, uncertain about this or that or this chunk of it, even though we know a lot. But I think it's important to recognize that unsettled science is not unsound science. That's real science.
Sure. You mentioned a problem with grant proposals in prediction. You have an issue with prediction as well. Let's talk about that a little bit.
It's not so much that I have an issue with prediction. I mean, I think the great thing about prediction is that it's predictably wrong, typically.
Right.
That we're so bad at.
That's what I had. I was going to say, there have been times we'll get back to this, but there have been times in science when people proclaim that something is settled, finished, over.
Oh, yes.
The one that comes to my mind is in the 60s, the Surgeon General said, infectious diseases are finished. We've
really?
conquered them. Yes. And
Really?
of course, yeah. Because we had antibiotics. They seemed to be working. There was not much resistance. And then everything exploded. And now, of course, they'll never be gone.
Right.
But there are other areas in science, and you talk about a few of them in your book, where people have claimed that this is solved, right?
Yes. Well, even people today, I think, would probably say, if you said geography, they'd say, well, that's not really science, is it? I mean, that's all pretty much settled.
Right?
But we know where. How many times can you discover America, as they say, But it's not at all true.
Yeah,
I mean, we still have the geography of the oceans. We have planetary geography. We have all sorts of new ways of mapping things. Some of the most sophisticated computer programs now are actually aimed at geographical mapping of things, So, no, these things almost never seem to really close, or when they become closed for a time, it's just because we haven't figured out what we don't know yet.
That's the key, really. Science is never finished. We never will understand everything, because when you do discover something, it just leads to more questions.
Often that's right. It opens up a whole new tunnel, another black room with some more black cats that maybe are wandering around in there, or maybe have already left for some other place. Who knows?
Okay, so back to prediction.
Yes.
A grant is a way of predicting what you think is going to happen, right?
Yes, and I guess this is tied up in the notion of hypothesis, which I also maybe...
You hate that too, that's right. You actually wrote that, I hate
hypotheses. Well, I've grown to hate them.
You didn't hate them when you started out, probably.
No, they seem like a reasonable idea then, but I think they've become something that that inappropriately runs the show. I mean, I think they've even become misunderstood by scientists, let alone the general public. So of course, the original idea of a hypothesis is Popper, the philosopher of science, said the trick is to have a falsifiable hypothesis. I mean, what you're supposed to be doing is proving it wrong.
Right.
And that's the only way a hypothesis is really of scientific value. Otherwise, they become little bits of, little belief systems, little clubs, little cults. Because after all, a hypothesis is your best idea of how something probably works. Well, who wants to be wrong? Who gets paid for being wrong? Unfortunately, very few of us.
So you think we set it up to be right?
Well, I think so, to some extent. Even if you work against it, I think you can't be completely unbiased. It's foolish to believe we can be. So naturally, you think of the experiments that are likely to prove it, or you look at the data a certain way. You have an excuse for throwing this outlier or data point out, one way, reason or another. Tuesdays, nothing ever works on Tuesdays, whatever, silly. And sometimes they're good reasons. I mean, you did have a junior person new in the lab working on the experiment. They got that crazy data point, so out it goes. But it may very well be because they're a junior person working in the lab who hasn't yet been indoctrinated in the way to do it, that they got that interesting outlier, and that's really where we ought to be looking. So I think hypotheses are difficult that way. And of course, my personal huge objection is because I'm a biologist and get money from the National Institutes of Health, as you do. And as you know, NIH grants are supposed to be written as hypothesis-driven research.
Right.
And as you know, the worst comment you can get from a review section is, well, this is just a fishing expedition, or this is just curiosity-driven. And I'm thinking, really? Are we all on a fishing expedition here? I mean, who are we kidding? And what's worse? What's better than curiosity-driven?
So you think that we should abandon this idea that every proposal has to be hypothesis-driven?
I do, yes.
And we can have, because look at what people are doing now. They're sequencing the microbiome of different human surfaces and cavities, right? Isn't that a fishing expedition?
Absolutely, fishing expedition.
It's really interesting, and that's why we're doing it.
Yes, there are going to be some fabulous fish that come out of this.
And that's because we're going to have 1 billion questions come out of that, right?
As you can see, I mean, so we thought the genome was going to answer a bunch of questions about genomics and genetics in humans, and it has. But what it's really shown us is that only about 10% of the genes that reside in our body. I mean, if you ground a person up, as it were, I'm not suggesting that, mind you, but if you just ground a person up and, sequenced all the DNA in them, you'd find out that 90% of the genes are not human. They're bacteria, viral, plasmodia, whatever they are, somebody else is living in there.
Yeah, I think that the whole way that at least NIH gives out money is flawed, and I see so many proposals. If you don't have everything lined up, and so the reviewers can tell what's going to happen and it'll work, then you're never going to get money, and that's terrible. That's not the way science. You should be doing experiments. You should be doing research, right?
Yes. Of course, I mean, the only upside of that is that they give you the money for 5 years and then they don't bother you really.
You can do what
and
you want.
You pretty much do what you want.
So if you can play the game at the writing stage, then you can do it. And that's, in fact, what most people do, right? They go off and do other things.
Of course. So it's, grantsmanship and gamesmanship, but that's not the way the system ought to work. And it's a shame because the system is very close to working appropriately if it, were just either a little bit better funded or a little bit, I mean, it is ridiculous. What's worrisome about NIH is all the fabulous research that doesn't get done. I mean, what's the difference between a grant that's in the top 15% and the top 16%?
No, there's nothing. In fact, up to 30%, I would argue, they're all really worthy.
I mean, this is already a highly selected population. You can't put a grant in unless you're an investigator with a laboratory in some accredited institution. So with a PhD, so at the very least, it's not like a normal bell curve even.
So in your field, do you do olfaction still?
Yes.
Okay.
Yes.
And I presume you write your grants in a hypothesis-driven way.
What choice have I got?
But if you could write a fishing expedition, what would you do? What's something that you could do?
Well, we did sort of write a little bit of a fishing expedition. It was a genomics grant when the first sequences of human and mouse genomes were becoming available. We were interested in specifically the olfactory genome. It turns out that there's a whole large number of receptors in your nose that detect all these odors, and they're the largest gene family in the whole genome, and they're very much like receptors that are used many other places in the body for detecting dopamine and serotonin and acetylcholine, all these chemicals in the brain that that we now think make us depressed or happy or this or that, reward, etc. And they're very similar, so we thought this is a really interesting area to be in now. And we simply wanted to fish around in the genome and pull out all these olfactory receptors and so forth. And that was a grant that went through and was a very successful program, because it was it was criticized as being a fishing. In fact, I wrote the grant and I said in the grant,
it's a fishing
I know this sounds like a fishing expedition, and it is, but it will definitely produce data that will be of use. I just can't tell you what the use will be for sure.
Right.
And they sort of swallowed that, but that's the closest I've ever gotten.
So if I wrote a grant application to say, I want to go and catch mice and find out what viruses they carry, it probably would never see the light of day.
No.
Because it's a fishing expedition.
Right. Yeah.
But it would be really interesting.
It certainly would.
For a number of reasons that you could elaborate, and you could make it compelling, but still they would say, but what's the hypothesis?
Yes.
Right?
Yes.
So that's problematic, and I don't think we should do that. I think really that grant applications need to be much shorter, and they should depend largely on the investigator and the track record. Give us a general idea what you want to do for the next 5 years. Looks good. This person's productive. Give them the money.
So the last part of it is I'd go even a step further with you, and I'd say you have to spend a little bit of time and effort writing your first grant that should lay out a research vision, what you see as being, identify several critical questions that you believe the tools are available to work on, and therefore you would work on them. And if you get the funding, then you have 5 years and you see how productive you are. And that grant should simply be renewed based on productivity, because there's really no other decent measure. I mean, if you've been productive for 5 years, then give them another 5 years. What's the worst that can happen is the last 5 years, the person's not productive.
Then that's it.
And then that's it, right?
Yeah, sure. I agree with that. I think the idea of, at least the length of applications has decreased, right?
Yeah, thankfully for that.
The other thing I wanted to explore with respect to funded science is this, you talk about it as a dichotomy between basic and applied research. And the applied part, I guess you mean translational, which is the buzzword that we use now. And we had a fellow here not too long ago, John Udell, talking about science careers. And he said translational research is actually not research, because you just want to see if something does something, and you don't really do setting up a question and trying to answer it. So you say that they're both the same, right?
Well, I think they are in the best cases, and I think that he's right in the sense that translational research is itself and at its peak the final stage of it or whatever, is maybe not research. It's an engineering kind of solution or something like that, maybe. Yeah. But I think what's the best kind of translational research, and I'm not against translational research. I love the things I like. Having a flu virus vaccination and things of that nature, So that's good by me.
Yeah.
But I think translational research is a kind of basic research that already decides it has a point. That is directed towards the possibility of translation. It's devoted to a specific disease, not to an underlying fundamental process of how cells work or things of that nature. How the Higgs boson is nobody can imagine what it'll be about, but who knows. In the future, right? I mean, Charles Townsend, who was a member of the Columbia faculty in physics in the 1950s, invented the laser, was ridiculed by his faculty, by his fellow faculty. I mean, there are these famous stories down there. People telling me, stop, what are you messing around with this collimated light nonsense for? Get to work on something useful. You're not going to get tenure. Man invented the laser,
Yeah, there's so many stories like that.
Yeah.
Tac polymerase, Thermus aquaticus, right? Who knew what that would be?
Right.
Go look at these hot areas and see what's living in them.
Yeah, well, retroviruses. I mean, that was a chicken virus, right? It was a poultry experiment, right?
You have to let smart people
That's right.
do what they think is interesting.
You have to let them fish.
That's the only way that...
Yes.
And you have a good section of your book where you give a lot of examples of things that happened, serendipity that turned out to be really useful. And that goes back to prediction, right?
Yes. Although, let me just say a quick word about serendipity, because I think it's sometimes used in the wrong way. Okay. I like serendipity. I mean, I agree that an awful lot of what happens in science seems to happen kind of somewhat unpredictable. But it's also true that it's not pure serendipity. I mean, lawyers don't make serendipitous scientific discoveries, and scientists don't make serendipitous judicial ideas either, or have them. So I think you have to be on a search. You have to be there. It's more like, who was it? Was it Jacques? No, it was Pasteur who said, chance favors the prepared mind.
Of course.
And of course, Pasteur was the beneficiary of a great deal of serendipity, but he's right. He was thinking about it. He was thinking about something. He was out on a fishing expedition, as it were.
You have to, I think you say it in your book, you have to be asking good questions.
That's right.
You can't just be randomly looking here and there.
No, and hoping for the best, right?
No.
Something will fall on your head.
I mean, I like to cite restriction enzymes. In the 50s, people knew that if you took DNA from one bacteria and you put it in another, it would get digested. They wanted to know why. But they weren't thinking of making recombinant DNA.
No.
They just wanted to understand what, and maybe they get a clue about immunity or something, right?
Yeah.
It led to restriction enzymes.
Yes,
but in itself,
it was
good science.
The whole biotech industry and all of molecular biology, yes.
It was good science.
That's right.
So that's your point. You have to have good science. You're not going to just wander around.
There's a great story about Albert Einstein, maybe apocryphal, but when he first got to Princeton, he was being interviewed by a reporter from the Princeton newspaper. Somewhere during the interview, the reviewer, the student said, well, Professor Einstein, do you carry a notebook with you to write down all your great ideas? To which Einstein supposedly responded somewhat sheepishly, to tell you the truth, I don't get that many great ideas.
That's great.
But how many do you need? I mean, 1% of the ideas coming to fruition would be a bounty.
Yeah. I don't know if I would have answered it that way. That's why he's a better scientist.
Yeah.
I would have said, I keep these notebooks.
I never look at them, but
I never look at them again. Well, I think it's good to write them down, even if they're not good ideas. I like, there's so many things. Here's another one. So there's a joke in your book about looking for keys under a lamp. Can you tell us that and how that fits in?
Sure.
Great.
It's a sort of a classic one. I think that many of us tell graduate students, and it's a story supposedly of a scientist, although I've heard it of others too. But I always use it as a scientist who's standing around outside by cars there under a lamplight and looking on the ground. Clearly he's lost something, and a passerby comes by and says, did you lose something? And I help out. He says, I lost my keys. I can't find them. So they look, and 5, 7, 10 minutes goes by. They don't find them. Finally, the guy says to the scientist, are you sure this is where you dropped them? And the scientist says, no, I think it was down there. And he points to some dark corner of the street. And I said, well, what are you looking here for? And he said, well, the light is so much better.
It's great.
And it's perfect, It's
perfect
exactly
science,
what you do. Yes.
That's right.
Yeah.
That's what Einstein also said it in a different way. I have no respect for people who take a board, find the thinnest part, and put all holes there.
Yeah.
It's the same idea. You do
exactly.
You have to go beyond your comfort area or what the field allows you to do, I guess.
Yeah.
That's really it. Another thing I wanted you to talk a little bit about, which is all models are wrong, but some are useful.
George Box, I think.
That was what he said, right?
Yes.
And so talk a little bit about models. So in biology, you use a model to study olfaction.
Sure.
Right?
We all do. And I guess I always think that when you talk to students to begin with, and then when and if you have an opportunity to talk to a wider public, it's one of the most important ideas in science to explain to people, because I think it's one of the easiest to be misunderstood. Because people think, well, you work on the brain, why don't you just work on brains? Well, brains are hard. I mean, brains are, it's a hard thing to work on. It's big. There's a gazillion cells in it, and they do a lot of complicated things. So more sensibly, using the light from the lamppost metaphor, if you will, we work where the light is a little better, where you can do something in a somewhat smaller system that nonetheless seems to be a good model for the larger system. That if you learn some fundamental things about the smaller system, you'll have learned something about the big system too, and then that lets you move up the ladder a step or so. And so we use these model systems, but sometimes they can sound quite silly or strange or funny or like a waste of taxpayer money. And that's kind of the problem with them, I suppose, and that's what we fail to communicate clearly, that choosing the right model system is one of the most critical things a scientist can do, because you've chosen a system that's amenable to making discoveries, to experimenting, to manipulating and understanding. And even though it's not the thing itself, it gets you a step closer to that thing.
Do you think most non-scientists understand that we can't do most of our research on people, and therefore we have to use, say, an animal? Or is that even hard?
I think even that may be hard, or whether it's valuable to do. Of course, now the idea of the laboratory mouse is sort of part of the culture, and I think people do sort of understand that, because you read it in the paper all the time. Somehow or another, we went from guinea pigs to mice. I mean, there was a time when guinea pig meant just that, right? An experimental
Don't be a guinea pig.
right? You know,
Sure.
Almost nobody uses guinea pigs anymore that I'm aware of, to tell you the truth. So, but what I think the public often doesn't know is that there are many other interesting systems one could use besides mice that seem weird. I mean, I started my career off studying the sense of smell in salamanders. Now, it's not because I care how salamanders smell particularly, but I understand somebody could look at my grant proposal, title of my grant proposal, which says the molecular physiology of olfaction in salamanders, and go, this is my tax money? I'm paying for this nonsense? And so it's easy to make fun of, but there are good reasons to do it in salamander before you try doing it in a mouse or even a person, It's a simpler system. They're cold-blooded and easier to maintain. They're not endangered. They're all sorts of
But people
reasons.
Will not understand that unless it's explained to them.
I think that's right. And it's a hard explanation to make.
And
I agree.
A science writer, journalist probably won't be able to do that, right?
No, I don't think they have an appreciation for it in the same way that a working scientist does.
And the real key is, let's say you discover things in the salamander. How do we then figure out if it's the same in people?
Yes.
Right?
Yes. Well, how many times have we cured cancer in mice? I mean, no mouse ever need die of cancer.
Right. So that's the leap that is harder to make, right? I mean, I personally have trouble explaining it to people how we get from mice to people.
And it doesn't always work. Of course, one of the ways that we can explain it, and I think it's a sensible way to explain it, is we believe in evolution. And part of the idea of working in mice in order to find things that will work eventually in people is that we realize that there's a certain continuity in physiology and in everything else about us, because that's how evolution works. Now, we're not perfectly continuous, because it's been 80 or 90 million years since we shared a common ancestor, so we've diverged significantly. But in the end, mice have a 4-chambered heart like we do. They have a liver. They have all these things.
And the olfactory genes in humans and salamanders are probably similar, right?
Yes.
At least structurally similar.
Yeah, they're structurally very similar. It's the same kind of a protein. And even many of them are, very, very similar. They've been retained because the same odors are out there in the world, now as when salamanders were.
So I guess if you want to develop eventually from your research products to help people's health, something to do with olfaction. I don't know.
Yeah, well, that's a hard one. I agree.
What's a drug that you could make that would target olfaction? Eventually, you have to test it in people. That's what I'm saying.
Yes, right? Yes. So
not all research goes to that point, but eventually, if you want.
Well, I'll give you a quick example in olfaction. So a couple of years ago, I was at a meeting, a biophysics meeting. I happened to pass by a poster. It was an anesthesiologist who was working on rhodopsin, which is the molecule we used to see with. But it turns out, I know this is going to sound crazy and I won't bother to explain it, but that rhodopsin, this molecule we used to see light with, is very similar to the same receptors we use for odors and dopamine and serotonin, neurotransmitters and all that.
Right.
So, and this was an anesthesiologist. I couldn't figure out what he was about, so I went over and piqued my interest. And we had a conversation. I said, well, let me ask you something. These anesthetics you work with, these inhalation anesthetics like halothane and isoflurane and all that, do they have odors? Because I know ether does. Ether has, even though we don't use it anymore. But he said, oh, yeah, they're very distinct odors. In fact, trained anesthesiologists will often use their nose rather than their equipment to be sure that all the gas is cleared and stuff like that. So I thought, well, if they have an odor, they must be activating receptors in our nose, just by accident, of course, because we have so many receptors in our nose.
Sure.
They're binding to some of these. But if they're binding to some of these, then they may be binding to other receptors in the brain that are like olfactory receptors, that are like the odor receptors. Now, I don't think that's actually how anesthetics work. I mean, there are lots of, it's 150 years we've had them, and we don't really have a clear explanation how they work. It's a great area of ignorance. And I don't believe that's how they work. But I do believe that may be where their side effects come from. That binding to these particular kind of receptors in the brain and elsewhere could be how the side effects come about from anesthetics.
Yeah.
So, it's kind of unexpected.
Yeah, sure. And so that is something that you could eventually test, but you'd have to do something in people.
Yeah, I think so. We know now that there's about 10 or so receptors in mice that bind these molecules, and we know there are similar ones in humans, and now we could go ahead and look for it in humans, yes. I
always make an argument that you can't use results in animals to predict what's going to happen in a human.
I think that's probably true, but it can put you on the trail.
Of course, it puts you on the trail, but eventually you have to do other experiments in people. The example I used last year, there was a brouhaha about avian influenza H5N1 in ferrets.
Oh, right.
And the fact that they could be transmitted through the air in ferrets, a lot of people took to mean that they would do the same in people.
Yes.
And that really bothered me because they're models. That's right.
There's no evidence of that.
And people say, but it's the best model. Well, it still doesn't mean that you can predict. And that's why I wanted to emphasize that you have to always take what you learn in your model and somehow figure out if you want it to be directly applicable to people. If you want to make a drug or a vaccine, you have to
really
people.
do it in people. I agree.
There's no other way around
like nothing else. Yeah.
There's another cool thing you said that I want to just bring up. Listeners will like it. Don't ask scientists what they do. Ask them what they're trying to find out.
Yes.
So you're sitting on an airplane, the person next to you, what do you do?
Yeah.
But don't you think that most scientists will actually say what they're trying to find out?
Yes. I think so. But the real trick is to not let them get away with that in a way. I mean, we've become conditioned to do that. We just dump a lot of data on people. That's what we're used to talking about. But if you really, I think the trick is, if you want to have a great conversation with that scientist, ask them what it is they're trying to figure out, not what they recently published or what they're doing. And the story I like to tell about that is this, I believe, true story that took place between Chaim Weizmann, the first president, I think, of Israel, and namesake of the Weizmann Institute, which is their big research institute in Israel. And he himself, he was actually trained, I believe, as a chemist, although I don't think he ever worked as a scientist. In any case, he and Einstein were on an Atlantic crossing together, ship, and I guess they were going to be on this boat for 8 or 9 days together. And Weizmann determined that he would spend every morning, Weizmann and Einstein would spend every morning for 2 hours sitting on the deck, and Einstein would explain relativity to Weizmann. And you think, well, this is a great idea, right? Wow, if only I had Einstein available, I could actually have him explain relativity to me. So at the end of 8 days, and having done this, they got off the boat, and Weizmann was reported to have remarked that he now believes that Einstein truly understands relativity. That was what but he had no idea, of course. But if it asked Einstein the questions that were now open because of relativity, what are the new ideas? What's going on with those guys in Copenhagen? And how is the world now how do we understand the world differently, then I think he would have gotten an earful, and he would have been fascinated by it.
Yeah, wasted opportunity.
Yeah,
I think that I've had some really interesting people ask me that, and then say, "But no, I don't want to know what you've done. I want to know what you're going to do or what you're doing." So it's the same idea, right? So to all the listeners out there who are not scientists, if you ever talk to a scientist, that's what you should ask them.
Yeah, otherwise, we'll bore the eyes right out of your sockets.
What is it that you're trying to find out? That's the question. So all of that, get that ready. So you think that, given that most scientists would be totally comfortable, right? They should be.
I think they should be, yeah.
Right.
I think they should be. I mean, after all, so people that come to my class often say to me, well, what should I do to prepare? I always tell them, no PowerPoints. For sure, no PowerPoints. What should I do to prepare? And I say, you don't have to do anything to prepare. You're prepared every day you walk into your lab every morning. Yeah. That's how you're prepared. Yeah. You're there with a set of questions.
Bring your curiosity,
that's how you come to the class, right?
At the Cafe Science the other night, there was a high school superintendent, actually, from New Jersey. And he says, what's the best thing you could tell kids in, say, high school or even earlier to make them or make sure they're prepared for science? And I said, make sure they're curious.
Absolutely.
Right?
Absolutely.
Look around the world and want to know how it's all working.
Yep.
Because if you find kids that say that, then they're the ones most likely to be scientists, right?
Yes.
Be curious.
Yeah, of course we beat that out of them pretty well. Peter Galvison pointed out to me the other day. I was having a conversation. He's a historian of science and an astrophysicist at Harvard. I had a meeting with him anyway, and it was a sort of a discussion at the table. And he said, "Well, the amazing thing to me is that in second grade, about 100% of the kids are interested in science, but by 12th grade, about 3% are. So we've developed this fabulous system for beating an interest in science out of our students. Apparently,
we give them too many facts." We want them to regurgitate facts.
That's it, and we select for the ones who can. And
yeah, exactly. Unfortunately, we don't teach them how the facts were obtained, which would be good.
Yes.
Right? Now, I had a great high school biology teacher who did just that because she had done some research. And I attribute to her the reason I'm in science today, or one of the main reasons, because she made it cool. Oh, well, wow, this is how you do science. You told us how you would go in a lab and set up an experiment and how careful you had to be. And that's what we need. But it's hard to do unless you've actually done science, right?
I think that's part of it. And unless you want to take the extra time and and of course, it's hard for teachers these days because everybody gets tested, and they get tested on the facts.
Sure. Facts.
But yes, but I always try and say what I think is a more effective way of teaching a subject is to try and recreate for kids the level of ignorance that existed when that discovery was made. I mean, try and put yourself back in the place of a Galileo. It's an interesting story about Galileo, who measured acceleration and gravity and all that. And one of the terms in his equation, which is simple but hard to remember if you don't care about it, is time, and time squared, in fact, as it turns out. And so that's all fine and dandy until you say to the kids, here's the only thing. There were no watches in Galileo's day. They hadn't invented timepieces yet. Yet people could measure a day or a month or a year, but there was no minute, there were no seconds, there was no stopwatch. How did he make these measurements, Oh, well, I don't know. I don't know. We didn't know about time. We didn't know about inertia. I mean, it turns out he used his pulse, and then he used a pendulum. And so you have to be clever. Well, once you learn that, and then you say, well, those awful inclined planes that you roll a ball down an inclined plane and measure. And what is that? It's so boring. I mean, it's so dreadful. But if you realize that the reason for that, Galileo, did that because he needed to slow gravity down. His pulse wasn't fast enough to just drop a couple of balls from head height. He couldn't measure it. But he could slow it down by putting them on an inclined plane. They would still drop through the same vertical distance, but take much longer to do it. And then he could work out a calculation.
Yeah.
And I go, well, that's a clever idea. How would you slow down gravity? Yeah, when you think of an inclined plane that way, it's interesting, isn't it?
Yeah.
Otherwise, it's just some boring physics
That's
experiment.
how you have to teach it to kids, and they would love it, I think.
I think so, too.
But not everybody can do that.
Yeah.
That's, I think, one of the things we have to do moving forward is try and get teachers at the elementary and high school levels to know more about how science is done, not just the facts.
Yes, and to give them the opportunity to do that. I mean, the problem, I think, now is that they're simply overwhelmed with the requirement to get through a textbook for a test that's coming up and an evaluation that will decide whether they get a raise or get fired.
As you said
or
earlier,
awful,
we have to change the way we evaluate.
We
have to change the whole thing. We do have a nice program here in the city. It's a Hughes-run program to get high school teachers in the lab for the summer.
I had one this summer in my lab. She was fabulous.
And they can be very good.
Next year, yeah.
And I've heard great stories of how these individuals go back and they do totally different things. And I think we need more of that. I'd be happy to have someone in my lab doing that. Do you find that having written this book, you were meeting different people than you would if you were just a neurobiologist?
I guess so. Yes.
Do you?
It's a funny. I've never written a book before. It's not typical for a scientist to write a book. I mean, a few do, but normally we write papers and all that, and we travel in an ever smaller circle. It seems. But so yes, it has been kind of interesting that way. I mean, it can take over a little bit. There's a side of me that would actually like it to kind of stop. I mean, you get caught up in this sort of slipstream of the book, I mean, people call you, they want you to come give a talk here or there. Right. I mean, the most interesting one, I suppose, was a fellow named Jeff Middleman, who's a rabbi in a synagogue in Westchester, New York, who wrote me and said that he had just read the book and he intended to use it as an inspiration for his Yom Kippur sermon. And I thought, well, that's kind of remarkable.
Sure.
So I wrote him back and I said, well, please send me a copy of it so I can send it to my mother, who will at least get a kick out of it. And he actually wrote quite an interesting sermon. I mean, it was rather nice. And we've since met. We had lunch together. And from a completely unexpected corner, I have to say. I mean, I would not have really expected from a religious corner. But I've gotten several phone calls and emails from priests, preachers, chaplains, rabbis, so forth, and artists that I would not have expected. So that's always pleasing, very gratifying.
So you can see that the book is having an impact and people are getting ideas from it.
Yeah, which is, I will say, very gratifying. One of the most interesting, I have to say very quickly maybe, is that an audience that I didn't expect, since we were talking about this a moment ago, an audience that I didn't necessarily expect, or I hadn't anticipated at least would be interested, are secondary school teachers. I've gotten, I'd say, half the emails I get, and if I'm on a call-in radio show, half the calls I get are from secondary school science teachers who say, this is what we need to be doing with our students. How can we do this? How can we introduce this into the curriculum?
That's great.
And I think that's fabulous.
No,
I'd love to see that happen. I feel so gratified by that.
I mean, you can make an impact in science, but when you go outside into the real world, to make an impact is really good.
Yeah,
right.
Yeah. So
that leads us to the last thing I want to talk to you. I know I've kept you more than any of your other interviews, but that's my style.
It's a nice conversation.
I like long form, and I think there's a subset of people out there who like it too. You make the point at the end of your book that scientists, we get money from the people, so we should explain to them what it is that we're doing. And they shouldn't depend on papers and other forms of the popular press to get their information. Why do you think that's the case?
Well, I think it's the case because, for the obvious reason that they pay for it and deserve to know something about it. It's clearly one of the key features of modern Western culture. I would say modern, almost global culture. I mean, it is true there are, I suppose, places in the world where science is not crucial or a part of the culture.
As far as they know.
As far as they know, that's right. But in general, I mean, I'd say science is one of the most important things in our lives. I mean, we're all quite happy to use the next gadget or take the next drug or a procedure and are happy for it. Yeah. And we should know something about this fabulous adventure. That is what it is. And it's only recently, I think, as far as I can tell from a historical perspective, that science has become so divorced from the public that both supports and uses it and would find it interesting. I mean, in 1800s England, and it was common for there to be performances. I mean, people would go to Albert Hall and pay money for a ticket to go see science demonstrations of magnetism and electricity and things like this and hear lectures on it. Darwin's Origin of Species was a bestseller. I mean, he was already wealthy, but he got quite a bit more wealthy on the sales of Origin of Species.
Weren't there public debates in Paris over spontaneous generation versus Pasteur? And that,
yes, and they would have big crowds. I mean, there was real involvement, and I think that that's healthy for one. And I think when you don't do that, then you. Well, my favorite story to tell in this, I guess, is the Galileo story, which we all think we know about. I thought I knew about it. You know, Galileo got in some trouble with the church fathers and all that, the authorities for championing this idea that the heliocentric solar system, that the Earth went around the sun and so forth. But actually, it seems to turn out that the what Galileo really got in trouble for was not so much the ideas, which there's fairly good evidence, I gather, that the church fathers knew as well, because they were the educated class as well. And it was in the wind. Everybody knew this was really going to be the case, but I think they hadn't quite figured out how to explain it to the populace yet. And what Galileo did was, because it was the height of the Renaissance and so forth, he published his book, the Dialogue on the Two Chief World Systems, I think it's called, published a book about this in Italian. The first time a science book had been published in a vernacular or common language as opposed to Latin or something like that. And that made it available to a much wider audience. And that's what kind of pissed the church off.
Right.
But it started a huge tradition of that. So Descartes wrote in French, and Hooke in English, and Leibniz in German, and so forth and so on. And so now the public became involved and interested in science. And I gather there are numerous historians who believe that this was actually crucial in the transition from the kind of magical, mysterious kind of world of the Middle Ages through the Enlightenment to the more empirical, scientific world of the Enlightenment. And I think we're seeing a reversal of that now. As science becomes less available to the public, we do see people going back for a kind of magical, mysterious explanations of events. So terrorist acts or hurricanes occur because there are too many homosexuals in New York or New Orleans or wherever, or we're not living the right life, or other explanations that are not real explanations whatsoever.
Why are we going backwards then?
Well, I think because science is becoming as inaccessible to the public now as it was when it was written in Latin. And that's, to some extent, our fault.
Which is sad, because the internet makes it accessible to everyone.
Yes.
Right?
Yes.
And there are things like TED Talks and podcasts.
And you see how popular those things are.
Yeah.
I mean, these TED Talks are amazing. They cost a fortune, and they sell out overnight, and then they're available online. So hopefully that's beginning to change. And there are people like you.
Yeah, there are certainly interest out there, and I think we could. I think you said less than 1% of the population does science. And is that in your book?
No, it's not, but I bet that's probably right.
I read it somewhere, and the rest of the world doesn't and needs to understand how it works. So you think the scientists are the best people to explain it, right?
Well, I do. Not every one of them.
Right.
We all have colleagues.
That's right.
I don't even want to talk science with them, let alone have them talk to the public. But that's true in every field, of course.
Sure.
But yes, I think there are scientists who are capable of communicating. One of the difficulties, I think, is that if you I worried about this when I wrote this book, and I'm sure you get this comment to some extent too, for the time you spend on these podcasts and putting this work out on your blog and all that. I mean, if you're a serious scientist, is this what you should be doing with your time?
Sure.
Or should you be at the bench? Should you be in the lab? Well, I think yes. If you're capable of doing it, or you enjoy doing it, and it works, then I think you're doing a great service to science.
Yeah, I tell people that you don't have to do as much as I do, but just do something.
Yeah.
Do a little something, and if all of us or most of us did a little something communications-wise, it would probably help.
Yes, at least people wouldn't flee from us at cocktail parties.
Exactly. I think that there is a big desire to understand science out there. Most of it's inaccessible. Science writing fills an important void, and I think people like it. The Science Times once a week, people really like that, because it's pretty well written science, but it's not coming from the heart, because they're not scientists. And I think that with a few exceptions, they're missing out. I think you made a point in the book also that a non-scientist can't understand the whole role of failure and how it drives science. You're fearing failure, but you do want to take risks and ask questions that you don't know the answer to.
Yes.
And if you haven't done science, you can't know that.
Yeah, my favorite quote in the book may actually be from Enrico Fermi, the famous quantum physicist, and who used to tell his students, apparently, that if you do an experiment and it proves the hypothesis, you've made a measurement. If you do an experiment and it doesn't prove the hypothesis, you've made a discovery.
Yes, I remember that. That was very good, yeah. I like that very much. One of my favorites is actually one I think we should close with. Getting comfortable with ignorance is how a student becomes a scientist. I like that a lot.
I think that's absolutely the case, don't you?
It is, but how do you teach that?
Yeah, I'm not sure how you teach it. I guess you... there's not a program that I know of for teaching it. You just,
right.
if you're in a laboratory, let's say it's a graduate student, which would be a little easier than teaching an undergraduate, because it's very hard to teach them that being comfortable with ignorance is a good idea, because they're worried about a grade point average. But a graduate student, at least, I think if you talk to them about what's failing, and you talk to them about the things that aren't working, and you spend as much time and interest on that instead of demanding that they get you the data to fix this hypothesis up to put it in a grant proposal, which is, some of our colleagues do. They run a tight ship. They run a lab where they expect, you put data in the hopper and papers come out the other end sort of thing, and that's the way they run it.
Right.
And I think that's not the way to do it. But I think if you teach a student by your own patience and your own interest in everything that they do that doesn't work,
and
not penalize them for any of those things that don't work, then they begin to appreciate that that's the real fun.
Right. Well, I think the book is absolutely brilliant, and as I said, the length is perfect. I think I'll give it to my lab for the holidays. I think every listener of TWiV should definitely read this book, and the more non-scientists out there that read it, the better they'll understand science. I mean, they're not going to understand the mechanics, but they'll understand the whole philosophy of really what drives discovery.
I hope.
So I want to thank you for writing it.
Well, I want to thank you for this chance to talk about
it. Like all other episodes of TWiV, this will be on iTunes at twiv.tv. And if you do like TWiV and the things that we do, go over to iTunes, subscribe, and leave a comment or a rating there. That helps to keep us visible, so we pick up more subscribers and help explain this science that we do. That's so important, as you heard today. And we'd love to get your questions and comments. If you have any for Stuart, I'm sure he'd love to answer them.
Absolutely.
Send them to TWiV at twiv.tv. Stuart Firestein is chair of biology at Columbia University. What is the official department name? Biological Sciences?
Department of Biological Sciences.
It's such a broad name,
I
isn't it?
know. What can I tell you?
But it's fine.
But if you just write the biology at Columbia, that works too.
That's right. Thank you so much for talking with me today.
Thank you, Vincent. It was a real pleasure.
I'm Vincent Racaniello. You can find me at virology.ws. You've been listening to This Week in Virology. Thanks for joining us. We'll be back next week. Another TWiV is viral.